In this first question, I'm always going to separate the numbers from the variables. So I'm dealing with 4 over 2, and I'm simplifying that fraction. And then separately, we'll look at how we simplify x to the power of 3 divided by x to the power of 5. Of course, we'll write the answer as a single fraction. 4 divided by 2 is 2 over 1. So I have a 2 left in the numerator and a 1 left in the denominator. When I look at x to the power of 3 divided by x to the power of 5, I can absolutely use my properties of exponents, or I can think of this as 3x's multiplied together in the numerator and 5x's multiplied together in the denominator. That shows me clearly that I can cancel 3 pairs of x's from the top and the bottom, and leaves me with 2x's multiplied together in the denominator. And let's try one last time. These 3 examples are a little more basic than what you would see on a module test, but they're a great place to start. In the first question, we have numbers and just x's. So we can simplify the numbers separately from the x's. We think of this as 4 divided by 2 as a separate problem from x to the power of 3 divided by x to the power of 5, although we will write the answer in a single fraction. 4 divided by 2 simplifies to 2 divided by 1, so that shows us that we have a 2 remaining in the numerator. For the x's, while we can use our properties of exponents, we can also think of this as 3x's multiplied together in the numerator, and 5 in the denominator. That clearly shows us that we can cancel 3 pairs of x's, and we're left with 2x's in the denominator multiplied together, which gives us x squared. So there's our simplified version of the first example. In the second example, we've got numbers, 14 and 7, but 2 different variables. So we'll treat these separately. So looking at the numbers, I have 14 and 7. 14 divided by 7 is 2, or I can think of it another way. I can think of it as the numerator and the denominator both being divisible by 7. 14 divided by 7 is 2. 7 divided by 7 is 1. Either way shows me that I have a 2 remaining in the numerator. In the denominator, I have x to the power of 2. It's the only x, and there's no negative exponent, so that x to the power of 2 will remain in the denominator. But the y in the numerator is raised to a negative exponent, and again, the negative exponent means we'll pick up the base and move it to the denominator. So there's our final answer. And with the remaining problem, I'm going to focus first within the brackets. Although we could apply the -1 right away, often our questions are much easier to solve, much more straightforward, if we can simplify within the brackets first. So we'll do that here as well. Again, I'll look at the numbers and the letters separately. Here I have 2 over 4, and once again, when I write that as a reduced fraction, I get 1 over 2. Again, it's as though the numerator and the denominator are being divided by the same value. That's exactly what's happening. 2 divided by 2 is 1, 4 divided by 2 is 2. So inside that bracket, I know I have a 2 remaining in the denominator. I've got an x in the numerator and a y in the denominator, and for the moment, there's no reason to move those. Themselves, they're not raised to the power of -1. That -1 is on the outside of our brackets. So I'll write x in the numerator, y in the denominator. As we discussed on the previous slide, now every single thing inside the brackets, the x, the 2, and the y, are raised to our exponent, which means that the x, the 2, and the y all move to the other side of the fraction line from the one they're on. So our final answer is 2y over x.